employee of H2O, and I moved from the UK to Silicon Valley back in March, so just coming up to 9 months here in sunny California, loving it, loving the culture. And so the overview for tonight, I'll just, so I'm guessing you're beginners, and I'll give you some examples from my background so you know what my biases are, show you some tools along the way, and a live demo of munging. So we hear a lot in the press about 80% of data science is munging. So what does that mean to me? How H2O fits in, what is H2O? And question and answers, just interrupt me anytime you have a question. Go ahead. So in nearly 20 years ago now, I joined Lehman Brothers in London, and I graduated in applied maths and computing, and this is one of the first data cleaning exercises I had to do. So the project was dividend claims. So in equities, dividends are paid on a regular basis, and they're paid to the company that is on register, on file, as owning that stock. But there's a delay between when the trade and then T+2, 2 days after the trade is when the registration changes. So what happens is claim dividends get paid, but they get paid sometimes to the wrong bank if that bank's sold that equity to the other bank. So the second bank claims the dividend back from the first bank, and that's the dividend claim. So the system was to track that. So you can imagine all the data errors. You've got people, in those days there was faxes coming in, and there's lots of zeros, millions and billions of dollars going through these claims, and people are typing it in. So there's fat finger errors, zeros in the wrong place, and claims on claims on claims to sort out the mess. And our job was to estimate the cash flows and predict who was going to be a good payer, who's a bad payer, those sorts of activities. So it's nothing fancy, there's no real machine learning in there, it's just really gathering the data together, producing reports, and making sure management know what's going on. So that was VB and Sybase in those days, and that was a production system, which to me means something that runs every night. So every night it would add up all the claims that day and then produce a report. And I created some messy data by making a change to the production system, and that ran that night in the batch. It was supposed to work, it didn't, and it doubled up all the entries into the main bank's ledger. So the next morning when the traders came in, all the numbers were way out, and they couldn't really work properly for the first 2 hours of the day, between 8 o'clock and 10 o'clock. So I was in big trouble when I got in the morning, because my colleagues had to clear up my accident, and then by lunchtime everything was back on track. So the traders were trading blind for a few hours. But 6 months later, when I went back to look at the data, because I'd created that messy spike, I knew to look for it and take it out of the data. So that's a very common occurrence. So if you didn't know that I had created that mess, then you wouldn't know to take it out. So that's what we mean by domain knowledge. And then I moved to Salomon Brothers, another bank in London, and here it was, we had a time series regression of all stocks, about 6,000 stocks in Europe, and regressing them, their monthly price returns against things like exchange rates, interest rates, and so on. So macroeconomic factors. And what we hear a lot in the press is that 80%, 90% of data science isn't the actual, the regression in this case, but all the cleaning up of the data prior to that. In this case, I definitely agree with that. There was about 5,000 lines of code, and only 2 was the loop through stocks regressing against all the clean data. So the euro came in on the 1st of January, but there was no history of the euro exchange rate because that was a new currency. And so we used the Deutschmark as a proxy prior to that, stitched that together to the euro, and then each month they would have to re-estimate the sensitivities of stocks to the exchange rate. So each month there'd be a new production run and a report of the new risks. And little things like the CDOLs going wrong. So is anybody here in finance or experienced CDOLs? So you know this one, these leading zeros, and people put an X before, is an Excel. When Excel exports, it drops the leading zeros, so people put an X to stop that. And if you don't, or you forget, sometimes you get the last check digit coming in as well, and you can easily join the CDOL to a completely different stock. So a CDOL 4455 with a different check digit is a real CDOL. So you can very, very easily get these kind of subtle data errors which affect your sensitivities. And then I moved to a different bank and did something a bit more exciting, which was pairs trading. And so the model there was to pick the 200 most liquid stocks and then look at all the pairs. So 200 times 199 divided by 2 is 19,900 pairs. Then run a test for stationarity of all those pairs on a two-year window. So there we did the Fuller test. And then look at all the pairs which pass that test, so they are stationary, and then back test what would have happened if we'd bought and sold the pair when that ratio crossed two standard deviations, a Bollinger Band around that ratio. So again, that's something that's running in production every day, producing 50 spreadsheets to 50 different clients, well, probably 20 or 30 different clients, but each client wants a different universe. So some want the stocks 50, others want the Europe, S&P 500, and so on and so forth, with different custom requirements. So that had to run every day, and that was in S+, generating the plots and putting that into Excel. So that's more data. That's the background. So then I moved to fund management in 2004, and then got to work with bigger data, say 25 terabytes. So this is a really good book. Does anybody know this book in finance? One person? So in here, this has a whole chapter on data cleaning and what that means for tick data. So what some of these sections will be looking at different types of trade. So for example, a trade may not be in an automatic trade in the continuous market, but can be an over-the-counter trade, and those tend to have a delay associated with them. So when you see them, and if you're matching them off against the prevailing bid-ask, they'll be far off the prevailing bid-ask. They'll be like 10 years ago, maybe 2 minutes gap. So that's the sort of cleaning that you want to do, is take the trades out that don't match the prevailing bid-ask, just to look at the automatic market. So that can get quite difficult, and there's some fancy math in there, but you can over-clean. So, and this happened to me, I queried this data for intraday auctions. So I did select from quote where bid is greater than ask, and got no results. So all bid less than ask, as you would expect, bid less than ask in the market. So I asked the data provider why that was, because I knew there should be some bid greater than ask. And they said, oh, well that was bad data from the stock exchange, and we removed it. And I said, well, did all that bad data apparently happen for 5 minutes? And they said, yeah, how do you know that? And I said, just to check, did the end of that 5 minutes coincide with a volume spike? And they said, yeah, indeed, how do you know? And I said, well, those are intraday auctions, and that's a crossed book which occurs in the market for illiquid stocks. And that's not bad data at all, that's absolutely correct. And we need to see that in the data to be able to do our data science. So I asked the data provider, can we have that data back? And they said, no, because we actually deleted it fully and purged it. So we can't go back and give you it very quickly. Or we can, but it'll be a new 6-month project, and we'll need to get management to go and authorize that. So we can clean. So my message here is, yes, there's lots of mess, and sometimes we can go overboard and clean away real data, which actually isn't messy. Another example was negative prices. They too can be correct. Some vendors in the finance space use to compress the data even more. They use the sign bit on the price to mean something. Perhaps an over-the-counter trade would have a negative price so that it could be easily cleaned away if you wanted to. So it's a marker that doesn't really mean negative. So you need domain knowledge before you even start to do data science. And the tools I've been using were KDB, which is great, and in-memory is the fastest in-memory database in that space for time series analysis. And you can download that and look at Q. I highly recommend just having a look at the Q language from their website, and you can use the 32-bit version for free to get used to that language. And the other product in that space is OneTick, which is similar. Any questions so far? Those are the kind of backgrounds from the information from my background, so you know where I'm coming from. So everybody knows R probably, and Python, SQL. This has come to data science and command line has been a new thing maybe the last 6 months. Jerome Jansen has written this book, and there's this video on YouTube which is an hour and a half long and goes into lots of great detail. So here's how to string together a pipe of commands at the Unix prompt. So the great thing about this is you can do that independently of, you can do that as a step before R or Python, so it's very efficient. And let's have a look at some of the commands that he put in his book. I think there's 80 Linux commands. When I saw this, I was amazed at how much you can do at the command prompt. And so, how many people use Unix at the command prompt? So 6 or 7 people. So these are really useful. I recommend just going through them. I'm often amazed when I ask people how they learn. Then I get the answer that I get varying answers. But the way I approach this book is the very first thing I did is I looked at the index. So if you want to learn a book, you look at the introduction, look at the end, go through every line of the index, and you can see what's in the book. And then you can decide what speed to read it, dip into it, look at all the commands. So I would start with this, and then just go through all the commands to make sure you know them and know what they do. So things like parallel can be used to start up parallel jobs in Unix without having to script it yourself. Curl, most people know for downloading web pages. Sed, awk, but there's also things like CSV cut. So you can just take a CSV file and cut it by column. CSV join, you don't even need to load it into a database or into R or Python. You can do the join from Unix. What else? We've got little r, which is a way of scripting R more conveniently straight from the command line. Obviously Python can be used from the command line. Paste is a Unix command. Sorting, so you can sort fly. I find that people don't know that you can sort at the Unix command line, which saves time, because all you want to do is order a file by a particular column. Then it's going to be much faster to do that at the Unix command than loading it up into R or Python and then sorting it. So loading up all the columns that you don't really need. Unique, word count, WC, I use that a lot. Word WC minus L counts the number of lines. in the file. So you can do that before trying to load it into R or Python so that you can have an estimate of how long it's going to take or how much it's going to fit. So that's those are Unix commands.
Good question.
Yeah.
When you speak of Unix, do you include Linux, Mac?
Yeah.
Also,
Yeah.
okay.
But all of these, I tend to use Ubuntu, Linux, but I think these all.
So Mac has it too. Mac OS X, because lots of people use Mac now, Apple.
Yes, I think all of these are on Mac as well.
Homebrew has most of them. Homebrew has the ones that don't
Oh.
ship with it.
So, well, I think on that point actually, the reason I use Ubuntu or Linux I actually have it running on a Mac. I use the Mac for the hardware and Ubuntu for the consistency with servers. So I'm using the same operating system on the servers that I do on my local network.
But if you didn't use Ubuntu, have you tried those with Mac? Or?
I haven't tried.
I recognize many of those commands, but
Yeah.
some of them, I have to try it at home.
Yeah,
Later.
yeah. So then, right, so the main message of this talk is messy data. And so there is this package, tidyr by Hadley Wickham, which is really good for dealing with untidy data. So this is how he defines it really well, which is that column headers are values, not variable names. Multiple variables are stored in one column. Variables are stored in both rows and columns. Multiple types of observational units are stored in the same table. And a single observational unit is stored in multiple tables. And then the solution is to gather, separate, and spread this data. So that's all about the shape of the data, getting it into a shape that you can then run your machine learning algorithms or your grouping or your joining on. But that's not the kind of untidy data that I'm talking about. I'm talking about the messy data in the content of the data itself. So you've already got perfectly tidy, regular, rectangular, simple data, but how do you find that situation where I duplicated? You remember at Lehman Brothers, nearly 20 years ago, I made this mistake and put too many rows into the database and made that production error. How do you find those erroneous duplications? How do you find the outliers and the data that shouldn't be there? Or if you leave it there, will it change your results? So I'm going to illustrate what I mean by using some public data. It's quite difficult to find public data that is messy because people usually tidy it up before putting it into the public domain because they don't want to put out messy data, obviously. So this is about the only example I know that contains messy data, just by chance. It happened to come up this year. So it's the download stats of R packages. And on R bloggers, how many people follow R bloggers? A few people. So people are obviously interested in which are the most popular packages. So that if you're learning R or Python, then you want to know what's everybody else using. So you want to use the same, so that that's probably got more coverage, it's got less bugs, and there's more support on Stack Overflow and so on and so forth. So there's 154 people have put blogs out with rankings of package downloads from R. And this is one from March 2015. And so this chap, Ozag, I think his name is put the ranking, and the most downloaded package was RCPP, which is because it's used by so many other packages. ggplot2, that's not a surprise. That's a very popular plotting package by Hadley Wickham. Everybody talks about it, so that makes sense. Digest, maybe. Reshape 2 is popular. Plyr, yes. Java, that's a strange one. That doesn't really make much sense being number 6. String R, yes, that's another Hadley package. And then some others. So it's okay, but a bit strange. Some of those names there. And then there was a tweet, and Data Science Central picked up on it, and they looked at the ranking that guy had produced, and then compared it to the number of questions on Stack Overflow, and said, well, that's strange. Data table, which is the package I wrote, isn't even in the top 100, and yet it's the second most asked about package on Stack Overflow in the R tag. So they made a conclusion and said, well, what does the R community need to concentrate on then? The packages which have the most questions, or the ones which are downloaded the most? And then other people were saying, well, data table must be really awful because there's so many questions about it, it must be difficult to learn. And it's not even downloaded very much, and so on and so forth. And this affected me, which is why I looked into it. And let's just step back a bit, because people go very, very far, very quickly. Because as soon as we all do it, as soon as you see a table of results on the internet, you believe it, don't you? Well, you shouldn't. That's the message. So let's have a look, and look at the small print. Right at the top, what's that say? So here is a list based on downloaded data for a single day, February 28th, 2015. So I went to this calendar and looked at what day of the week was that. Well, that was a Saturday. So this ranking is based on one day, a Saturday, February 28th. So, what was this guy thinking? So, can I do any better? Can I just have a look at the data? So let's do it, and that's what I'm going to do now. So, let's see how easy it is to confirm the data yourself and clean it. So, here I'm using GEdit, just because I can press F5 and send the current line to the whatever's running at the bottom. So here at the shell, I can run shell commands, bash, Unix commands like we were seeing before, or I can run Python, or I can run R, all in one place. So I'm just going to place my cursor up there, and press F5, and I cd into that directory. And let's have a look in there. So I've just downloaded all the files from the RStudio mirror, and let's have a look. So I've gone right up to yesterday. The first thing I'll do is I'll just scan through and look to see the size of all the files, make sure there's no zeros, because it's quite often the case that a download fails, or was cancelled, or accidentally copied. So I'll just scroll up with the mouse wheel, just eyeball this number here, and look at the figure going up as I go up. So, okay, I seem to have data, and I could load it into R and Python and have a look at the distribution of that size of file. To be absolutely correct, you should do. But I'm just going to eyeball it. Okay, so that's good enough. So let's start R. I'm just going to use data table because that's the package I know best, but this would equally be as good in pandas or dplyr. So now let's load up that date. So we just freak that date and look at the file. So the text has wrapped around here because I've made it big for this screen. So let's remove some of the columns, and if I scroll up a bit, well, let's not be interested in the R version, the architecture, or the operating system. So let's remove those columns. So in data table, the thing after the comma is what you want in the columns. So we want to take away these 3 column names, and with means we're just taking the names away by name. So let's have a look at data again. This is the main point. So here we have, let's first look at the number of rows. So we've got 192,000 rows in this one file for this one day, the 2nd of February. This is a little check. So yes, the date in the file matches the name of the file. So quite often in finance, well, not quite often, but sometimes you get a situation where the file's been misnamed. I had a time when we had CDs from the exchange, and they sent us one CD per month, and they accidentally saved the same data from March into the April CD, and it was all the same data. That's actually really hard to spot. And in that case, I don't remember whether the date was in the file itself as well. But it's also always good if the date, because some people will think, oh, well, this date's the same all the way through the file. Let's save a column and save some space by just missing it out on our CD. But then that causes more trouble than it's worth often. So it's better in that case, if it's just one column, then just leave it in for robustness reasons. So, okay, so I haven't got anything to compare to. I have no idea how many downloads to expect, but it doesn't seem wrong. It's a Saturday, so I expect 992,000 to be quite low compared to history, but we're only looking at one file. So this is the day from that particular that particular ranking. So let's just have a look at the ranking. So here we've run this command. So we've just .n is just a symbol which means the number of rows by package. So it's grouping. And so these packages have this many rows in the data. And it just names the column n corresponding to the .n. So the first thing is it's come back not in order. So we've got 700 and then 1,000 and then it goes down to 8. So let's sort it. So let's sort it by this count. So now we've got the biggest packages at the bottom and the smallest at the top. Let's change that, be the other way around. So there we can order by -n instead. So now we've got the top packages first. So if we go back to the website that Basil created, it's going to be awkward on the side screen I have, but this is what I find myself in finance doing all the time, is that I create some data at the prompt here, and then I want to go check I've done the right thing. So let's have a look at that page. 1960, I'll just use my eyes, 1960, 1785, 1709. That's about as much as my brain can remember. Let's go back to the prompt. Yeah, those are those three numbers. And if we keep on going, then it's exactly the same. So that was quick. We reproduced exactly what he came up with. But what do we do now? Well, let's have a look at just, what I often do is just have a look at the data again and say, well, let's do something random. And that's, instead of grouping by package, what else can we group by? Well, there's this IP ID at the end. So why don't we just have a look at the data and describe the data by all the columns, look at the cardinality of all the columns, the maximum, the minimum, the distribution of the columns. So just as a simple example, let's just group by this IP ID instead. So this is on the RStudio webpage. It describes that it's an obfuscated IP address. So each day, all the unique IP addresses are given a number from 1 to however many IP addresses there are. So let's do that. Group by IP address. So some people, this person, well, this IP address has downloaded 259 packages. Sounds reasonable. Somebody else 3, somebody else 68. So we're just looking at the top and the bottom, but there's this huge distribution in the middle. So let's not just rely on the top and bottom, and let's just do the ordering once again. And here we can find the most active ID. So here's IP address 884, downloaded 12,000 packages on this one day. That's odd, because there aren't even 12,000 packages in R. There's about 6,000 or 7,000 as of that date. So let's have a look at that IP address. So let's just look at all the rows of data for IP ID 884. So let's first of all check the number of rows. Yep, 12,409, so that's what we think we're looking at. That's right. Top and bottom rows, so they're downloading different packages, and that seems, that's not very helpful at the moment. So what else can we do with that? Well, why don't we look at this IP address, 884 again, and just group its downloads by package, and then sort by the number of packages it downloaded. And here, now we've got, so it downloaded, the most times it downloaded a package was twice. And so because we ordered by n, we know that the middle of the distribution here is between 1 and 2. There's the 6,325 packages. So what's happened is probably they downloaded all the packages. It stopped 70–80% of the way through because the Wi-Fi went down or something, and then they downloaded it again to get a full download. So maybe they were creating a CD. Apparently, universities download all packages and create a CRAN mirror on a regular basis and pass that round to their students for courses. Other CRAN mirrors must download from other CRAN mirrors to get the packages or something. We don't know. No idea why that idea is downloading so many packages. So why don't we go back to the original question that I asked, which is sometimes difficult to do, but it's easy to get sidetracked and start looking at all the data and forget why you even started in the first place. So we were looking at, the tweets were that data table isn't even in the top 100. So let's compare data table to dplyr, which is what I was interested in. So we look at dplyr, so all the package dplyr, count the number of observations by IP ID, and then order it by, in reverse order, the number of rows. And so we find this guy, IP address 28, has downloaded dplyr 48 times. And so is another ID, and so is another ID, and so is another ID. So finally we're starting to get to some strange, messy data. So the message presentation is that this is tidy data, it's one table, there's no NAs in it, but there's some mess. So let's have a look at that particular IP address, number 28, for dplyr. So package equals data table, and the IP address is 28. And then let's just have a look at the top. So there's the 48 downloads, and just eyeball it. So we've got time 53, 23, 23, 52, 52, 23. So this IP address seems to be downloading the package every half an hour for some reason. So maybe it's checking it, maybe it's obviously on some kind of timer. I've noticed that on GitHub, when you commit when you push any commit to GitHub, then the build will run, and that will download all the dependent packages first, and that will hit the CRAN mirror. But that's not regular. That's whenever you push a commit. So I'm not really sure what this is.
A continuous deployment, maybe?
Sorry?
Continuous deployment in Jenkins, for example, that every 30 minutes, and it pulls.
Well, I don't think Jenkins is every 30 minutes.
You can configure it, right?
Right. It could be something like that, yeah.
Why is that the 1552 is ahead of 1522? There were a couple of places. The sequence.
Yes, so this one is now out of sequence, exactly.
Why?
So that's a good question. It'll just be the way that the file has been written. So this will be, the data here is written in the order. The query the data table returns always returns it in the order that it appears in the file, in the data. It retains that order. So you could do a sort by that timestamp. But there's nothing, nowhere in the instructions does it say that the time has to be monotonically increasing. And that's something that's definitely, when you load time series data, check it's actually ordered, because if you start doing a difference on that time series, it's going to be out, if it's out of order, it's going to be the wrong result. So those are definitely checks to make. And then let's look at data table and see what's happening there. Oh, well, that's not happening for data table. So I might be onto something now. So the way I think about this now is, well, I could go into this particular file and try and work. I could ask questions on the internet. I could fire off an email to ask them about this particular data. But usually it's quicker just to come up with a quick fix, a workaround, or just something pragmatic, so that we don't have to get delayed in looking at this mess. So what can we do to get some sensible results out, and just adjust the data without having to properly fix it? So one thing we can do, let's have a look at the count by package again, order it by the number of downloads. So this is the same ranking that we saw by that chap Basil. And let's look at the ranking. So RCPP is the top, ggplot2 digest. So that's the same ranking we saw before. Let's make an adjustment. Actually, let's just look at dplyr and data table. So we see the data table is just outside the top 100, and then just by one rank, as chance would happen. As chance would have it. So what adjustment can we make? Well, why don't we just say each IP address can only have a count of 1 per package per day. So that IP address, which was downloading packages 48 times in one day, let's just count 1 hit. We're still going to have duplicates because the same IP address is going to download the package day after day after day, but at least we get rid of the main problem and just see what's going on. Or rather, make a small improvement. So here we go, we're going to count the number of rows by IP address and package this time, and then count the number of those rows by package. So they were just doing the same ranking but adjusting. And then look at dplyr and data table. And this is disappointing because data table's rank has gone down now. It's 104. So is dplyr, but it still isn't in the top 100. So although I'm positive that I found the root cause of what was going on, making this adjustment hasn't helped. But we've still only 1 day. So let's step back for a moment and do something else here. Rather than here. Oh, I'm merging here the previous ranking to the next ranking. So I merge the previous answer to the next answer by package. So that's the key column that we're joining by, and we're looking at the old rank, this column, and the new rank. So some of the ranks are changing, but we're just looking at the top and the bottom here. So let's order this change in rank by the absolute change in rank here. And look at which packages move the most to see if our adjustment has made any difference. So Shiny has moved from rank 56 to 97. Our Java, which I said was a bit of a surprise, has moved from 6 to 42. And dplyr moved again. Anyway, so there's some moves here. So something's happening. But let's step back for a moment now and look by month and go over time as the final thing. So we've got all the data as files, 1 file per day, going back to the beginning of January. This is a little R function to generate a sequence of values. So sprintf is from C, so we can use 0%02 to pad 1 with a 0 there, and 11 doesn't get padded because it's already width 2. So those are all our text strings for our months. And we loop through all the months, and then we get all the files that match that pattern, apply the fread function to it, and then rbind list all those files together into one table, dt. So that dt will be a file for the month of January and the first iteration. Then we'll run the query that we were looking at before, so we'll count the number of rows by date. We have to include date now, so that we just count one IP address per day within that month, and package, and then count those rows, and then order the result by the most downloaded, and then put the rank on the end as a column so we can look at the differences in rank. And then we'll print the ranks data table dplyr. And so this is something I do maybe before lunchtime, and so this might run for some time. So I do it as a for loop like that, so that I can see when I run it like this, then it's doing the first month first, and so I don't have to wait for all the results to come back before I can even start to look, but I'll see the result for January come up now, and I can see, okay, so dplyr was ranked 35 in January and then 74 for the data table. So this is looking better, and it's what I wanted to see, because data table is now in the top one. So I've got my result. And now it's looping, it's gone on to March, and I'll just sit here watching it, and the first few iterations look good, so I'll go for lunch, and I'll come back and I'll have my results at the prompt. Now I forgot to create one result, but I could stop it now and change my for loop to save the results as it's going along, or I could just throw away the for loop and do it in one go. But anyway, we see the ranks coming back now, and this is a little bit better. At least we've got some average across the days in a whole month now, not just one day and one Saturday. And we can see some stability over time, that the ranks aren't changing too much. And yes, dplyr is more popular, and it is being downloaded more. We can reach that conclusion. And then August, let me just leave it running so I've got my prompt back. But we can see the number of downloads. So it's not very many downloads, 47,000 versus 40. That's September. So I might, if I've got time, I'll write this up into a blog post and put that out there. But to date, nobody else has cleaned this data. So we do occasionally see yet another tweet or a blog post where somebody's just done the raw ranking and has adjusted it. So this is what I mean by cleaning data. Yep, that's the end of that. Any questions on that? So how does this all fit in with H2O? So big data used a lot. This term's overused. I prefer just to work in terms of gigabyte, actual numbers, gigabytes. So if there's three cases of big data in my mind. If the data really is bigger than RAM, so it's greater than 240 gig, it won't fit in the biggest EC2 instance. So that needle in a haystack, looking for fraud, where sampling and throwaway data will change your results, so you don't really want to sample. The data is medium and it fits in RAM, but it's compute intensive, and you want to replicate that data across other nodes and then use more cores. Or the data fits in RAM and feature engineering results in more data. So So an example of that is with the pairs trading, where I started off with 200 stocks, I then ended up with 19,900 pairs by looking at all the combinations of pairs. And then we need speed for production, so scoring needs to be fast enough and to be useful in real time, and in research we need to be able to interact with data. We can't run a query or machine learning algorithm, we need to wait for a whole day to come back. If it can come back within 30 minutes, that makes a real difference to your workflow, whether it fits in one day or not. So there was this website that came out a few months ago. Anyone see this one? Does your data fit in RAM? So it was just this was the entire website, was just these words and this drop-down box. So you kept on dropping down. It started off with 32 gig, I think, or something. So I kept on increasing it, got to terabytes, and it still said, yes, your data fits in RAM. And 6 terabytes was the biggest. If you went to 7 terabytes, it said, no, it doesn't. So then you followed the link, and it takes you to this machine, which is the Parage 920. It's got 60 cores. On the website, you can get a price for 1.5 terabytes, but it's got 96 slots, which you can put up to 64 gig in each slot, which makes the 6 terabytes in one machine. And it cost about 150 to 200,000. But it's still only 60 cores. And in the H2O office, we have 10 machines, each with 32 cores, so we have 320 cores and 2.5 terabytes of RAM. And we find that many businesses already have this commodity hardware and want to use all the cores. So what have I been doing recently, just to finish off, is so data tables, radix join, I've parallelized and distributed in H2O in Java. So an example is a 1 billion row table joined to another 1 billion row table, returning 1 billion rows. A data table takes about 10 minutes. H2O on 1 node, 3.5 minutes, and H2O on 4 nodes, 1.5 minutes. And so that's what I'm just going to show now. Notice that with 10 nodes, it's not faster because the overhead of communicating bytes at some point on this size. So there's usually a sweet spot of the number of nodes which is optimal. So let's play this. So the data's already been created, and what I was aiming for here is to use all 32 cores on each of the machines. So that's the green bar, and then as those CPUs are working, then the white bars on the right are the data transfer between the machines. So I want to get as much bandwidth used as the CPUs are working as possible. So this bit where there's a lot of blue, I'd be looking at the algorithm and trying to make it more green. And so what it's doing is it's taking the 1 billion row table, which is distributed across the 4 nodes, joining it with another 1 billion row table, which is also distributed across the 4 nodes, and then returning a new 1 billion row table, which is also distributed across the 4 nodes, and it's 5 columns by 5 columns, returning 9 columns. And so the thing with this is the single table doesn't have to fit in one machine. The input, the 2 inputs and the output can all be bigger than one machine. And so that's basically a big join. And it's just about finishing now. And then it returns the data in sorted order. Sorted order is very important for time series and joining to the prevailing observation, things I didn't really go into. And it's basically the same data table concepts but scaled up. That was all. Any questions?
Yep. What's the distribution style of the 2 tables? Are they
distributed to all nodes equally, or are they sharded, or?
Yeah, pretty much. It's pretty much equally. Yeah. The first head of the table is more distributed, and then it starts to go in chunks.
And are they co-distributed, or do they share the same key?
No, they can be independently keyed.
So worst case, they're entirely sent across the network in the process of join?
The whole table, no. So it's a radix join. So the first step it does, it needs the first part of the key to be, it'll look at the distribution, and it'll just transfer the keys.
Oh,
Then it'll join the keys, and then it'll work out which rows need to come from which nodes, and then gather it all together. So the thing about this is that the first step is doing some data transfer straight away, whereas other algorithms will, if given a distributed table, it'll sort each node first and then merge. This is different. It's implicit. It's using bandwidth right from the start.
So in the data munging example that you showed, you had few MBs of files, and then you went through multiple steps to see what is there and what patterns the data is in. So if there is a data which is like hundreds of GBs, how do you find that you are confident enough with the data to start with the analysis phase? When do you decide that you are confident enough? Because there could be some patterns of data or some wrong data which is present there, and you have not reached there yet through, say, 5-10 examples.
Well, you're never really 100% confident that you've got everything. You're just always coming up with ways of trying to look at the data in different dimensions, trying things that you wouldn't expect to work and doing them anyway, looking at the columns randomly, grouping randomly. Hopefully you have some sense of what correctness should be. So in finance, if it's a trading algorithm, you would put it live, even though you knew there was some, you hadn't got it quite perfect yet. And then you would refine it as new data came in, and if it didn't work and it didn't make money, then you would switch it off after some time. And often, when it goes into production, indeed, it doesn't match backtest, and you would compare backtest to your production, and rerun production, match them up, and if they don't match, then you know you've got something wrong in your data collection, or your storage, or your conversion from backtest into production, or something like that. No. Depends on what you're doing and how critical it is. Great, thanks very much. It's quite difficult to pitch a munging talk because there's so many different products, backgrounds, and implications of all the different what's munging anyway, and people know SQL. So I thought it was interesting to see my background anyway, and the way I approach it. So, approach that. Great, thanks for coming.